Welcome back to this next problem. This problem is about computing power. So let's see what this is about. For example, if I provide input x as 2 and n as 3, then the output should be 8. Why is that? It's kind of like calculating 2 power 3. So what is 2 power 3? It's 2 into 2 into 2. So 2 into 2 is 4, 4 into 2 is 8. Okay. And similarly, some more examples. When x is equal to 5 and n is equal to 3, we are calculating 5 power 3. So 5 into 5 is 25. And 25 into 5 is 125. And when we do 5 power 0, it should be equal to 1. Okay, so this is the idea of computing this power. And let's start off with a naive solution. The clue for the naive solution is that we will just run a loop from 0 to n minus 1, or if you want, from 1 to n. And inside this loop, we will just do result is equal to result into x. Okay, I hope I have given you more than enough clue. Try to solve with the coding exercise. We'll meet again in the solution video. Hey, welcome back to this video. We will try to solve the computing power problem in a naive way. Okay, so let me create a new file. So 11 computing underscore power.js. Let me create a function called computing power, and this is going to take x and then n, which is x power n is what we are trying to calculate. Okay, and then I'm going to initialize a variable called result, and let's initialize it to 1. Now let's start a for loop. This loop starts from 0 and it goes till I is less than n, and then we increment I each time. And inside this loop, what we will do is like result is equal to result times x. So each time we multiply the result by x. So how many times this x will be multiplied? N times. And at the end, we are just going to return the result. So let's add some test cases. Console.log computing power of 2, 3. Let's copy it a couple of more times. And 5, 3. And probably 3, 0. Okay. What are we expecting? The first one should return 8. Second one is 125 and third is 1, right? Okay, so node 11 computing power, yes, as expected. That's the output. What is the time complexity of this? Time complexity is like we are trying to run this n times, right? It's based on this n, so it's kind of like big O of n. And what is the space? Here we just don't use much space apart from this constant result. So I mean one variable result. So we can say the space complexity as big O of 1. Okay, so in the next video, let's work on this in a more efficient way. Welcome back to this efficient solution. So this is going to be the first efficient solution, which is going to use a recursive approach. So let's say we are trying to find out the power of x power n. Now the idea of this solution is that depending on the value of n, there are two cases. If the n is even, then what we are trying to do is like we will just calculate power of x, and then we will do a floor of math.floor of n divided by 2. So we are just trying to cut the problem by 2 whenever the number is even. And once we calculate this, what we will try to do is like we will try to create a temporary variable which is nothing but a multiplication of itself. For example, temp is going to be equal to temp into temp. After this, once we know that's temp, we will calculate temp is equal to temp into temp, and then we will return back. But if the case is odd, then what we are going to do is like we are going to calculate based on power of x comma n minus 1 into x. It's correct, right? Because we know odd is like, for example, in the case of 2 power 3, right? The solution is going to be 2 power 2 into 2. And in order to calculate power of 2, 2, we can make use of this even case. Okay. Now at the end, we are just going to return the value. So in order to give you a more clear picture, power of 3, 5 is going to be power of 3, 4 into 3. And 3 power 4 is going to be power of 3, 2 into 3, 2. So let's get to some idea about how this recursion call stack is going to be. Let's say we are trying to calculate 3 of 5. And initially we will say power of 3, 2. And this will again call 3, 1. And this time this is, remember, odd. and this time again it will call 3 comma 0. 3 comma 0 is going to return 1. Okay, and this is going to return again 3 comma 0 is 1 into 3 to the parent, 3 comma 1. 3 comma 1, if you remember, what it will do is like it will again return 3 into 3, right? So we have the return value of 3 and then it returns 3 into 3. And in the main function, what we are going to do is like it's going to call 3 into 3, since it's odd, right? 3 comma 5. So we are going to return 3 into 3, 3 into 3, and then 3. Okay, this is how the whole solution is going to work. If this is a little bit confusing, don't worry, we will tackle this in the solution video. Please take this idea and try to solve this on your own in the solution video. Okay, welcome back to the recursive efficient solution. Let's tackle this. So let me create a new function. So function computing power 2 of x comma n. Okay, and inside this, initially what I'm going to do is like I'm going to add the base case. So here the base case is if n becomes equal to 0. If it is 0, then we will just return the 1. So this is the base case. Next, what I'm going to do is like I'm going to create a temp variable and then assign it to computing power of 2. We are just calling this function recursively. So x, we will pass the x, but this time I'm going to do math.floor of n divided by 2. So this will keep on running until computing power or n becomes 0, right? We will come back to this again. Now once we are out of this, what I'm going to do is like I'm going to say temp is equal to temp times temp. Okay, now that we have this temp dot temp, what we can do is like if n percentage 2, if n is divisible by 0, basically if it is equal to 0 triple equals, then we know we have an even power, which means we can just return the temp. If it is an odd power, then we will return this temp multiplied by x. Okay, that's all actually the problem is. So let's copy this test cases. Let's try to run this. Node 11 computing power. Yeah, we get the same output. So basically what's happening is like initially, let's take the example of 2 power 3 or maybe 3 power 5 itself, right? From what we see here, 3 power 5. So we come here, n is not 0, it's 5. So we call computing power of 3 comma n by 2, 5 by 2 is 2.5, and at flooring it gives us 2. So we just call back power of 3 by 2. So it will again call itself, n is not 0. This time it will be computing power of 3 comma 1. So 3 comma 1 is called. And again, this will be called computing power, this time 3, and then 1 by 2 is 0.5, and hence flooring it will become 0. So when calling power of 3.0 again, this times it comes inside this base condition and hence it returns 1. Okay, so now computing power of 3 comma 0 has returned the value 1, which means it comes back to the power of 3 comma 1. Now the temp is set to 1. After that, what we do? We just do temp is equal to temp into temp. So 1 into 1. So temp is still 1. Now we check whether the power is an even or odd. We could see clearly that this is an odd. So what we do? We do 1 into whatever that x. So this times 1 into 3. So we just return 1 into 3 to power of 3 by 2. Okay. So now what happens? 1 into 3 is returned, right? So basically now power of 3 by 2 has temp value as 3. Okay, so now we do 3 into 3. Now we check whether power is an even. Actually this should come here, guys, this return value. I have made a small mistake. Yeah, this should be somewhere around here. Okay, happening. And n percentage 2 is equal to 0. So now we return just 3 into 3. Okay, so now 3 into 3 comes back to this 5. So when we have 5, we calculate again. We already have 9, right? 3 into 3. So we again do 3 into 3 into 3 into 3. Okay, and since it is also an odd, we again multiply it by 3. So if you see, we get 3 power 5. So that's what we are returning over here. This one, 3 into 3 into 3 into 3 into 3. This also has to come over here, guys. Yeah, sorry. So that's how this solution, recursive solution, works. So what is the time complexity? As you could see, this goes for log n times, right? Basically, time complexity is big O of log n, and similarly space complexity is going to be big O of log n. Okay, so let's in the next video go over the iterative solution, because we know always iterative solution takes less space. So let's see how that works. Okay, see you in the next one. Welcome back to this video. In this video we are going to talk about this efficient solution for computing power using iterative approach. This iterative approach is completely different to the recursive approach which we saw in the last video. So what is the logic behind this? The logic behind this is based on this mathematical principle that every number can be written as a sum of powers. So basically, if it is 3 power 10, right, then we can call it as 3 power 8 into 3 power 2. Similarly, for 3 power 19 is, it's going to be 3 power 16 into 3 power square into 3 power 1. So if we just sum these powers, then we will get the 3 power 19. But what it has to do with this computing power? That's where we are going to make use of this bits or binary representation. This iterative approach is also called as binary exponentiation. So how are we going to do this? Let's see. For example, take the example of power 10. 10's binary representation is 1010. Okay, and 19's binary representation is 10011. So here is where our logic comes into the picture. So take the for example of 1010, and we are trying to do calculation for 3 power 10. The first power is nothing but 3 power 1, and second is 3 power 2, and next is 3 power 4 and not 3 power 3. Remember, it gets incremented by 2, or power of 3 into, see, 3 power 1 is 3, right? So 3 into 3 is 3 power 2. 3 power 2 into 3 power 2 is 3 power 4. 3 power 4 into 3 power 4 is 3 power 8. Now, whenever the number is equal to 1, right, binary representation is 1, the bit is 1. If you try to calculate those values, it's 3 power 2 into 3 power 8, which is 3 power 10. Again, for the clarification, let's take the example of 3 power 19 as well. So it is 3 power 1, 3 power 2, 3 power 4, 3 power 18, 3 power 16. Now let's take the bits which has 1 as value. 3 power 16 into 3 power 2 into 3 power 1. You see, it's the same representation over here. So now that I have given you a clue of what we need to do, try to make use of this fact and calculate the power. If you're not able to solve it, don't worry. We will see you in the solution video. Thank you. Okay, welcome back to this iterative solution. Let's see how to solve this. So as a first step, let me create a new function called computing power 3, and this is going to take x as well as the n. And as a first step, let me initialize the variable result to 1. Now here comes the logic. So as you remember, we need to loop over this binary representation of this power, right? It's not the x, it's the x power n, so which is the power. What we will do is, like, I'm going to say this, there is a loop which is going to run. So this is going to run until n is greater than 0. So until n is greater than 0, now what we need to do is we need to get the last binary representation value. Okay, how can we get this last binary representation value? It's actually easy. We just need to check if n is divisible by 2. So n mod 2, if that is not equal to 0, then we know we have a binary representation with 1 and not 0. Okay, if it is 0, then it will be divisible. If it is not 0, then we know it is going to be having a binary bit as 1. So now that if we have 1, what we need to do, we just need to update the result to result times x. So if this is not the case, then for all other cases, irrespective of like whether it is 1 or 0, if it is 1 we do this, if it is 0 or 1, then after computing this, what we are going to do is we will update the x. This time, if you remember, 3 times 1 is 3 square, and next iteration it becomes 3 power 4. So what we need to do, we just need to multiply x by itself. Okay, so for example, let's take this example of 3 power 10. Initially it is 0, right? So n percentage 2 is equal to 0. It will not be, result is not updated, but then we are doing 3 times 3. So now it becomes 9. Correct? For the next iteration it is 9. So now then when it comes to the next time, we again check. Okay, there is one more step before this. If you see, now we have calculated this last binary bit. So now we need to move to the next bit. We need to get rid of this bit. So in order to do that, if you have been familiar with high school mathematics, right? How do we get this binary representation? For example, take 10. We divided by 2, we get 5. And we again divided by 2, we get the 2 and then 1, right? We again divided by 2, 1, 0. So this time 0. So if you see, we are getting 1, 0, 1, 0. So as you could see, we just need to divide the number by 2 in order to get the last bit out. So what we will do here is that we will also follow the same. So n is equal to math dot floor of n divided by 2. Now when it comes to the next iteration, it will check whether it is not equal to 0. If not equal to 0, then the result is updated, and again we multiply it by x into x, which means if it comes as 3 power 2, the next iteration will be 3 power 4. So we are just trying to increase the power by 2. Okay, cool. So that's all. So let's try to update the test case and see whether everything works fine. Okay, looks like I have made a mistake. Oh, okay, it's capital M. Okay, I haven't returned the result, so return result. Now, yes, as expected, 8, 125 and 1. What is the time complexity of this approach? This is also going to take log n times, but the space is big O of 1. Okay, great. So see you in the next video. Thank you.